Welcome back. We're doing homework problems for our Thermodynamics 1 course. This is homework number 5, which is energy balances or first law analysis on open systems. Okay. And so number 5 says, assume a toluene behaves according to the following equation of state. Okay. So let's see, where's our equation of state? Because it's not on here for some goofy reason. So we're going to go to the original to find what our original equation of state should have been. So I'll have to change that on the wiki. Okay, so our equation of state is B equals RT over P minus A T over P squared, well, whole thing, quantity squared. Okay. Where A equals some value. So the toluene flows over an electric heater at 350 Kelvin and 50 pascals. So I have a pipe here, I have an electric heater, and I've got toluene flowing over this thing. Okay, so I've got toluene coming in, I've got toluene coming out, it has an equation of state. Let's see here. This is an isobaric process, so P in equals P exit. That's going to be one of my assumptions. Assume isobaric. Let's see here. Toluene flows over an electric heater, 350 K and 50 pascals. So this is 50 kilopascals. T in is equal to 350 K. I want to know what T exit is equal to. Molar flow rate is 150 moles per minute. Okay. If I want to do that per second, that will be, well, let's say 5 halves, right? Yeah, five halves. So that'd be 2.5 moles per second. Okay. All right. The heater is a 15 kilowatt heater, so Q is coming in here at what did I say? 15 kilowatts. Okay, so 15 kilowatts. Okay. But the lack of insulation leads to a heat loss at a rate of 200. So I have two Q terms. I have Q of my heater, and then I have Q loss. Okay. And that is approximately 200 watts. Okay, so 200 watts. Yeah. It's not well insulated. And I want to know what's the final temperature of this guy. Okay, well, so I'm going to assume it's isobaric. I'm going to assume it's steady state. I'm going to assume there's no work. I don't really see any rotating shafts. There's electrical work, but I like to consider that more of a heat term. Okay. But I don't have any rotating shafts. I don't have any boundary expansions. I don't have anything like that. Okay. I'm going to assume that there's no leaks. I'm also going to assume that delta KE and delta PE are approximately 0. And that's about all I can assume. Everything else is going to have to be in depth. Okay. So I'm going to do my mole balance, which says that summation of ins, n dot I minus summation of exits, n dot E equals dn dt of my control volume. That goes to 0 because it's steady state. There's no leaks, so there's only one thing coming in, there's only one thing coming out. Oh, they happen to be equal to each other. Fancy that. And we'll call that up. Okay. And then we do my energy balance, so summation of n dot I, h I plus v 1/2 v squiggly squared I plus g z I minus summation of n dot e h e plus 1/2 v squiggly squared e plus g z e, okay, plus q dot plus work dot equals d u plus e k plus e p d time control volume, that goes to 0 because it's steady state, that goes to 0 because there's no work, that goes to 0, that goes to 0, that goes to 0, and that goes to 0 because there's no kinetic energy and potential energy. So I have n dot I h I minus n dot e h e plus q dot equals 0. Okay, which we're gonna kind of combine some terms and stuff. So we have so let's see, what do we have? We have q dot loss plus, so this is really minus 200 watts because we're losing it, q dot loss plus q dot heater equals n dot he minus hi. Okay. And I want to find a temperature. And so I'm going to have my, q dot L plus q dot H divided by my molar flow rate is equal to my delta H, which is, because this is a real system, I need a departure function. And so this is a departure function, so I'm going to draw a departure function thing. Well, I have V as a function of T and P, so I'm going to have P and T, and so I'm going to go from here to here. I'm going to go down to 0 and up, so this is 0, that's my ideal gas. And so this becomes minus delta H departure function okay, at the inlet stuff, so Ti and Pi, plus delta H of an ideal gas, plus delta H departure of T exit, P exit, okay. And then I'm gonna need my departure function, so I'm gonna erase a good chunk of this to get my departure function stuff. Okay, so just practice departure functions. We'll do this one. So what do I have? I have, gosh, how do I do this? Well, I've got delta H departure function. I'm going from an ideal gas to a real system, and I've got dH dP at constant T because I'm taking an isothermal pathway dP. Okay, departure. So this is equal from 0 to P, dH dP constant T minus dH dP constant T of an ideal gas. That equals 0 dP. So dH dP at constant T is equal to TdS dP constant T plus VdP dP at constant T. That goes to 1. This is equal to oh gosh, is that minus? Yeah, so this is minus T dV dt at constant P plus V. Okay, and so my integral is going to become from 0 to P of V minus T dV dt at constant P dP. Okay, so I need dV dt at constant P, so dV dt at constant P is equal to R over P minus 2AT over P squared. Okay, and then from that, I'm going to plug that back into here. So I have 0 to P of V, so I have RT over P minus A T squared over P squared minus T times that guy, RT over P. Those go to 0 because that's the ideal gas contribution, plus 2AT squared over P squared. Okay, so when I'm all said and done, I can pull out the minus, the AT squared. So I have AT squared, 0 to P, going dP over P, P squared. So this becomes minus 1 over P from 0 to P. Okay, so I have, times AT squared. Okay, so I have minus AT squared over P plus AT squared over infinity. Over 0, which this is pretty much infinity. Okay, but the thing is, I've got infinity plus something, but then I'm going to have minus infinity minus this thing. And so the infinity is essentially going to cancel itself out. Okay. Because this is not a real equation of state, is really what it is. It's not a real equation of state, so it shouldn't work out the way it's supposed to work out. Or the way it does work out, rather. And so when it's all said and done, I'm basically going to have, AT squared over Pn plus infinity, okay, or rather minus infinity, because it's minus. I'll do this one, minus AT exit squared over PE plus infinity. And now these cancel out, and I'm good to go. Plus my heat, which is Cp dt of an ideal gas, okay, from T inlet to T exit. And I'm going to do all that integration nonsense. Let's see here, where am I at? I'm just trying to solve for temperature, right? Because it's isobaric, so I have that. I'll have this temperature, I won't have this temperature. This will give me some god-awful thing. And I can integrate, but man, it's going to be a cubic, and so I'm going to need a solver when I'm all said and done. Okay. So it's a pretty complicated problem. If I assume Cp is constant, that would be nice. Then it would still be a quark that I'd have to solve for because of the equation of state I used. But I would know it. Really all I'm solving for is delta H. So this is kind of like homework too. I'm just solving for delta H. It just happens to equal all those other things. Okay. It's like I know what they're equal to, and I just solve for a temperature based on that delta H. So, well, really it's like homework 3 because it's a departure.